We will now talk about the resistance of a conductor. What are the factors on which the resistance of a conductor like this depend on? Well, does it depend on the current? Conductors that obey Ohm's law are called ohmic materials. And for such materials, the resistance does not depend on the current passing through them, but depends only on the material of the conductor. Most conductors are ohmic when the temperature remains a constant. That means when the temperature changes, the resistance will change. So one factor that is going to make a difference in the resistance is going to be the temperature. The other factors are the physical factors of the conductor, which we will talk about in a minute. Resistance of a conductor depends on physical factors such as length of the conductor, area of cross-section, and temperature T. Now tell me, what happens if I increase the length of the conductor? Well, if I increase the length of the conductor, electric charges have to drift through a very long path. That means the resistance is greater. You see, if you have a very long corridor and a large number of people have to pass through it, as the length of the corridor increases, it will be much difficult for the people to reach the other end. So we can say resistance is directly proportional to the length of the conductor. Now, how does the resistance is affected by the area of cross-section? Area of cross-section is a measure of how thick the conductor is. If the conductor is very thick, the area of cross-section is large. Tell me, a large area of cross-section, will it increase or decrease the resistance? Let's go back to the analogy of the corridor. If you want to make it easy for the people to pass through a corridor, we better make the corridor wider. Is that right? Make it easy for people to go. So as the area of cross-section increases, it will be easier for electric charges to drift through. The resistance decreases. And so the resistance of a conductor varies directly as the length of the conductor and inversely as the area of cross-section. And of course, the resistance also changes with temperature. We will consider these two things differently, the physical factors and then the temperature. The resistance of a conductor is directly proportional to its length and inversely proportional to its area of cross-section. How do we write that mathematically? You can write it as R is, I haven't written the proportionality here. You can see this can be written as R is proportional to L over A, or R equal to a constant times L over A. So this is a constant for that particular material. Resistance of a conductor equal to a constant times length divided by the area of cross-section, where rho is a constant and it is called the resistivity of the material, the resistivity. Can you tell me the unit of measuring rho? You can see if you solve for rho, rho will be RA divided by L. The unit of resistivity is ohm meter. Can you get that from here? RA, ohm meter squared divided by meter, will give you ohm meter. So resistivity is measured in a unit called ohm meter. How does the resistance depend on temperature? As the temperature increases, the amplitude of vibrations of the atoms and molecules of the conductor will increase, which will make it difficult for the charges to drift through. That means as temperature increases, the resistance also will increase. Conversely, if you decrease the temperature, what will happen? A decrease in temperature will create more order within the material. There will be, the atoms and molecules will be more quiet. That means it will be much easier for charges to drift through. In fact, there is a study, a branch of physics called low temperature physics. And at very low temperatures, most materials will lose all resistance. At that time, when a material loses all resistance, it becomes a superconductor. In other words, no energy will be lost in transporting electric energy through those conductors. You know, a lot of energy is actually lost in transporting electricity from one place to another. You know, these big cables, the high voltage cables, the high tension cables that brings electricity to your local area from the place where it is generated. Now, they are resistance wires. Although they are good conductors, they offer resistance for the flow of electric current. That means a lot of energy is actually wasted in overcoming the resistance. If you can get those cables made of superconductors, a lot of that energy can be saved. Well, the science of producing superconductivity is superconductivity at low temperatures. Well, at the moment, superconductivity can be obtained only at very low temperatures. There are researches going on to see if we can find materials that will be superconducting at room temperature. Then we can solve that problem. And maybe some of you can take that challenge and do that research so that we can have materials that will be superconducting at room temperature. The temperature dependence of resistivity is nearly linear for all metals, except at very low temperatures. Now, the resistivity of a material at any given temperature is usually compared to its resistivity at 20 degrees Celsius and is given by the relation rho. Remember, this is the equation for the resistivity of the material. Rho equal to, that means rho at any temperature T. The resistivity at any temperature T equal to rho 20 times 1 plus alpha T minus 20, where alpha is a constant called the temperature coefficient of resistivity. A similar equation can be written for resistance. You can see resistance and resistivity. Resistance at any given temperature R is R20, means resistance at 20 degrees Celsius times 1 plus alpha times T minus 20, where alpha is called the temperature coefficient of resistance. Now here, alpha is a constant called the temperature coefficient of resistivity or temperature coefficient of resistance. Now, I have got some values of these which will be useful. I have given you the material and the resistivity at 20 degrees Celsius. So these are the values of the resistivity of some common materials like copper and aluminum. They are the most commonly used conductors. So those values are important. The resistivity of aluminum is 2.8 times 10 to the negative 8 ohm meter. And the value of its temperature coefficient of resistance is 3.9 times 10 to the negative 3 per Kelvin. And similarly for copper. We may need it when we want to use them for problem solving. Alright, let's do a problem. A resistor constructed of nichrome wire has a cross-sectional area of 2.4 millimeter square. When a potential difference of 12 volt is applied, across the ends of the resistor, a current of 0.0056 ampere exists in the resistor. What is the resistance of the resistor? What is the length of the resistor? Well, to calculate the resistance, we need the potential difference and the current. Is that right? When a potential difference of 12 volt is applied, there is a current of 0.0056 ampere. Can you calculate the resistance? Yes. Alright, we will start by calculating the resistance. The area of cross-section of the wire is given as 2.4 millimeter square. That is 2.4 times 10 to the negative 6 meter square. I hope you understand that conversion. The potential difference is 12 volt and the current is 0.0056 ampere. The rho for nichrome, I picked it from the table. Rho for nichrome is 100 times 10 to the negative 8 ohm meter, and those are our data. Now, in part A, what is the resistance of the conductor? R equal to V over I. V is 12 volt, I is 0.0056 ampere, and that gives the resistance of that conductor or that resistor as 2142.9 ohm. Alright, B, what is the length of the resistor? Well, we now have to recall the equation that connects the resistance of a conductor, how the resistance is related to length, area of cross-section and resistivity. Can you recall that equation? R equal to rho L over A. So R equal to rho L over A. We have the resistance, we just calculated. We have the length, we have rho, is that right? We have the area of cross-section, therefore we can calculate L. Solve for L. L equal to RA divided by rho, and put all those values that we have. That will be 5,143 meter. The length of that resistor is more than 5 kilometers. Alright, let's do another one. A wire with a resistor